Good afternoon, everyone.
Yeah. Good afternoon.
I welcome all of you here in the second session of today. And we have among us Professor Kamlendra Awasthi. Topic of this session is Polymer nanofilters for energy applications. And let me introduce our technical speaker for this session, Dr. Kamlendra Awasthi. He received his PhD degree from the University of Rajasthan, Jaipur in 2007. Dr. Awasthi is an assistant professor in the Department of Physics and is currently working as head Material Research Center at Malaviya National Institute of Technology, Jaipur, India. He has worked at Nanoscience Center, Indian Institute of Technology, Kanpur, India, as a research scientist and at the Lebanese Institute of Polymer Research, Dresden, Germany, as an Alexander von Humboldt Fellow prior to joining MNIT Jaipur. His main research area is soft material with a major focus on polymer nanofillers and nanostructured materials for photovoltaic sensor and nanofabrication applications. He has authored and co-authored more than 90 publications. Dr. Awasthi has edited the special issues in various journals like International Journal of Hydrogen Energy by Elsewhere, Bulletin of Material Science, Springer, Materials Today, Chemistry, Elsewhere, Materials Today, Proceedings, Elsewhere, Macromolecular Symposia, Willy, and Materials Letter X, Elsewhere. He is the organizer of a series of international conferences on soft materials held every 2 years from 2014 onwards. He is the recipient of reputed fellowships and awards like Young Scientist Award in 2008 by DST, Government of India, Alexander von Humboldt Fellowship 2009 by Humboldt Foundation, Germany, Inspire Faculty Award in 2012 from the Department of Science and Technology, Government of India, and Early Career Research Award 2017 from SERB, New Delhi. So we are really thankful to you that you spared your time for us. And now I hand over the session to you for your technical talk.
Okay, thank you, madam, for introduction. And I thank the organizer, Professor Ankur Jain, for this opportunity to talk to the audience in this meeting. So let's start my presentation. So can you hear me, or once let me know my screen is visible to you?
Yes, sir, you are perfectly audible and your screen is also visible.
Okay, thank you, ma'am. So today I'm going to talk about this polymer nanofilters. What are the challenges and application for this energy, particularly in hydrogen? So if we see our day-to-day life, how we are starting from morning to evening. So like for different life application, we are using a filter also, like for when we having tea and other things during daytime. But have you thought why we need different filters for different applications? So maybe like one common line solution, because of the size difference. It means we cannot use a single filter for the various applications. Okay, so means we need some kind of filtration that is based on the size. So what is the sizes of gas and how we can overcome, what are the challenges? So this is just the overview that I'm going to present in this talk. So I will talk about membrane, what types of membrane, why gas separation, and in particularly gas separation, why we interested in hydrogen, and this hydrogen, how we can separate from this trackaged membranes or block-copolymer nanotemplates or functionalized membranes. Then I will conclude my talk. So what is membrane? So membrane, just a selective barrier that we use between two phases, so that allow the movement of one to another side. It may be due to the force, concentration gradient, pressure gradient, temperature, electrical potential gradient over the membrane. So if we see our cell membranes that already exist, so what they do, basically they are also very selective, and they allow only one and blocking to another. So it means they are also selective, so that one can pass and other can be blocked. So this is the example of protein channel, and these are the phospholipid here. So can we mimic the similar thing in the synthetic membranes or in polymer membrane, so that they can allow only one gas that can pass through and other can be blocked? So idea is to mimic such properties in the synthetic membrane. So this is the first reported experiment on the membrane transport in 1748. So Knowledge has performed this experiment, and he used as a pig's bladder as a membrane. And what he found, like he has this water and a spit of wine in another side. So he found as this water permeated through the bladder faster than the wine. So it means it is allowing one kind of species faster and blocking to other. So this way you can think like this membrane basically is using just like a barrier between the two phases. So membrane structure, what type of membrane it may be. And this is also very old experiment and very popular. You can see in earlier days how to purify the water. So this is sand and gravel filtration technology, like where we have sand and gravel, and this way we can get our filtered water out. But this water, what is coming out, it has bacteria, viruses, some pollutants and salt. Why? Because these sands or the gravel, they are not basically, either they are absorbing or they're not selecting particularly this bacteria virus to flow throughout this permeate water. So what are the other applications of our daily life? Human skin. We filter the hot tea using a mass filter. There is a filter in juicer which filters fruit slag. The water you drink is almost certainly filtered to remove more. And your car contains filters for the fuel and air, and vacuum cleaner. So if you see this filter, it means there is something according to their size and what either we want to have based on size, or we want to go for like binding. So it means there are different type of membranes according to size or according to their nature. So their structure may be dense. Dense means there is no porous structure, but they have some internal free volume. Microporous membrane layer that is supported on another porous layer. So I will discuss this example in my coming slides. Okay, so membrane material we can have from polymers, metals, ceramics, liquid membranes. But in today, I'm only focusing about this polymer. So why polymer, not the others? Because once we have a membrane from polymer, this is flexible and some other advantage, but we can certainly modify its properties according to our application. And these polymers membranes can be made by isotropic, means solution casting, and so on, and anisotropic phase separation and other. I will discuss all these methods in my coming slides. And these membranes, they have various applications like in microfiltration, ultrafiltration, RO membrane, gas separation, preparation and dialysis, electrodialysis, liquid membrane, and so on. And today I will just cover this gas separation part, not the other application part. So this is like a overview of available membrane technologies. Means they have microfilter, ultrafilter, nanofilter, and RO. And here you can see the porosity. Once we are narrow down the porosity, the operating pressure that you can see is increasing. It means in microfiltration, we can only have clay, bacteria, large viruses, and solids. But when we go for other part, nanofilter and RO, here we are able to see this monovalent salts. Means this cannot be filtered by this microfiltration, ultrafiltration, and others membranes. But at the same time, when we are decreasing the porosity, we are going for a narrow pore size distribution, the cost of membrane is increasing. And after a certain time, we have to change the membrane, means the life also. So if the porosity is limited or very narrow, so one problem, the life of membrane, and second, the cost of membrane. So can we do something in this microfilter or in ultrafiltration membrane so that they can have the almost similar properties that exist in RO membrane? So this is the one challenge that we have for this water filtration. And similarly, can we use this microfilter or nanofilter membrane so that they can have a selectively absorb or can pass particular gas and other can be blocked. This is the in case of gases. Okay, so let's see in microfiltration, as I discussed, the pore size is near about 0.1 micron. So it of course need very low pressure, but it can remove bacteria and large virus. But for small viruses, protein molecules, we need to go for this ultrafiltration membrane. So here the porosity near about 0.01 micron. But again, it does not filter the ionic particles, lead, iron, and so on. So we need another kind of membrane. Then we come to this nanofilter. So it almost removes the toxic or unwanted iron, lead, or iron, whatever not possible with the ultrafiltration. But the cost or the monovalent side, they cannot be filtered by the nanofiltration. Then we need, of course, this RO membrane that typically we are using in our home for getting this water. So here the pore size is very less, 10 to power minus 10 meter or 0.001 micron. So if you can see, generally after 6 months or 1 month, we need to change this filter. And of course, it needs very high pressure when we are operating with this membrane. So how we can keep large particles from fouling membrane with the small pores? This is one challenge. So how we can do? So one possibility is there, like we can use a series of membrane, so that means larger part that can be filtered out at one level and second and third and so on. But again, the size of your module and the cost of module, this is again very high. So this is not a good idea to use all membrane in a series. Okay, so this is another example or story, like what we can do in this nanofiltration. So the nano membrane means 10 to the power minus 9. So they have very close to this RO membrane, but having less cost. So what we can do, we can decorate these channels with some other particles. So it means we can design a new nanofilter membrane so that they can catch particle, or we can insert particle in this membrane so that those particles means those are the toxic to bacteria. So here it gives an idea, can we make a nanocomposite membrane so that they have the similar properties as in RO. Okay, so now today I'm just going to talk on this gas separation. So why we this gas separation? So in particularly we need this hydrogen and nitrogen separation, basically in ammonia plant, and this hydrocarbon separation in petrochemical application, CO2 and water removal from natural gases, organic vapor removal from air and nitrogen stream. So we are using this polymer for gas separations because they have low investment, low weight, flexible, low cost, and high surface area. And those cars, they are running on this hydrogen fuel, they emit water, so means again no pollution. So why we are interested in hydrogen? Because membrane, they may be useful for purifying hydrogen because of their low capital cost, compact size, and easy to operation. And in fuel cell, there is one component to have this impurity in hydrogen. So how to get a pure hydrogen for this fuel cell application? But at the same time, if you see the kinetic diameter of the gases, this hydrogen 0.28 nanometer, CO2 0.33 nanometer, nitrogen 0.36 nanometer. Means their kinetic diameter, they are very close to each other. So like we cannot make a filter that like 28.9 nanometers so that it can go only hydrogen and can block, because whatever I'm talking right now, this is basically in the range of nanometer. So suppose if I say 50 nanometers, 60 nanometers, 70 nanometers, so you just see every gas is passing through comfortably. So how to make a selective nanofilter so that we can separate these gases? So certainly we can make polymer composite and other membranes. So when we talk about a membrane, so means ideal membrane that should have the high flux in terms of high permeability, and should be thin, high selectivity, mechanical stable, and this is should be like reproducible when we talk about on industrial scale, and of course it should be having low cost. So these are the most common inorganic materials to have in case of polymers. So membrane materials, they are biological or synthetic. And here you can see this organic and inorganic. So organic, they may be various type, but we can also make them hybrid by means combining this organic and inorganic. So we may make means composite, and we made them symmetric, asymmetric, and composite. And these techniques may be sintering, stretching, track etching, template leaching, sol gel, solution cast coating, phase inversion. So these are the various techniques to make this membrane from either pure organic polymer or from make them composite. So at last, solution coating and phase inversion, these are two popular techniques that are being used for making the membranes. So again, like there may be based on the material, we can use ceramic, zeolite, porous metallic, composite. But here I'm talking about this trackage membrane because here you have freedom to choose the porosity and pore size. And these are the membrane preparation techniques: stretching, trackaging, template, sol gel, phase inversion, and coating. And of course, further we can have some modification or engineering in any of these membranes. So sintering means just a heat process we can give, and we can make a porous membrane from pore size distribution having 0.1 to 10 micrometer. Another, this stretching. So here the pore size may be 0.1 to 3 micrometer, but please keep remember the pore means kinetic diameter of gases that we talk about around 28 to 30 nanometer. Porosity is very high, and because pore size is very large here, then the phase inversion technique that can also be used to making this asymmetric membrane. So here what we have a solution of polymer in poor solvent that prepared at a high temperature, and when we transform into final space, there is a sudden drop in temperature so that polymer precipitate, and then the solvent is pass out. Okay, so this is basically simple, but again, there are some constraint by using this phase inversion technique. So this precipitation by solvent from vapor phase and so on, and we can have this immersion precipitation. So here you can see we can have support, and this is polymer solution. We can have non-solvent and solvent, and finally one can evaporate, and you can get this membrane out. So this is a simple way that you can prepare your membrane. You can have a bath where you can have a uniform for maintaining this height, and this is the petri dish. Here you can pour your solution, and later on this solvent that evaporate, and finally you can peel off your membrane and you can get it. So okay, so let's talk about this trackage membranes, why we are preferring, because this pore shape, size, and density that we can tune, and this modification can be done by the shift heavy ion, so that we can make the HAL damage. So this is how we make a membrane. So like polymer, this is a, you can say, multiple, like a more chain like structure. So what happen if you have a high beam that is passing through from this channel? So you can see mostly the chains are break. So this phenomena is called chain seasoning, and once they join each other, so it is called the cross linking. So what is happening here, this is, you can see the dark part here. So this is the path of your beam, and this is the damage that is created along the track, and these material basically are loosely bound along this track, and you can remove it chemically, and you can make them cylindrical or conical depending on the size. So this is the facility that available in IUC New Delhi and another in TFR Mumbai, where you can do this kind of experiment for large area irradiation. And here you can see what is happening when this ion beam is coming through your sample. So this is the path of ion beam, and later on the damage that they have created, that can be removed chemically. So here you can get your porous membrane channels. But in case if you can etching from one side and stopping the other side, you could get the conical shape, not the cylindrical. So how this is, you can have various shape and size by changing the parameter or by changing the rate of chemically etching. So you can make a different shape in polymer nanofilters. And this is, you can see the SEM images of, this is the top view. This is 10 to power 8 ions per centimeter square. So here you can see some pores, they are overlapping to each other. And this is the cross-sectional view. So you can see your pore, this is through and through, and this is the cross-sectional view for a single pore. So you can see this porosity is same throughout this polymer. And once if you are etching from one side, so this is the cone-like structure in your polymer. So how we can make this cone-like structure and why we are interested in cone. So if you are etching from one side and stopping from the other side, so this is your current and voltage signal. So here you can see it is almost 0. It means these both chambers, they are not connected to each other. Once the current suddenly increases, it means they are connected and you should stop somewhere here. So this phase, basically this is in contact with this etching solution. So of course, it is like a cone-like structure, and once they are connected, so you stopped here. So this is very small opening. So you can consider means left hand side, this is the opening structure around in micron, few micron, but at the other side, this is the few nanometer. And this is as application in biotechnology, detection of biomolecule without any chemical and other treatment. So this is the current signal and without DNA. And once this DNA is passing through this conical membrane, so you can see this blockage, and this is the current discrete time. So by calculating this time, you can calculate the length of your DNA molecule. So we can tune the various shape and size by this voltage also. And this is one interesting phenomena, like being a polymer neutral, and it is showing a diode-like behavior in this membrane. This is because of the various groups, carboxylic group, they are presented along the pore wall. So this is the one reason to have this rectification. Okay, next, there are tubular form of membrane. So these are the hollow fiber membrane, and these can be made by tri-weight spinning, melt spinning, and dry spinning. So we can make such membrane also for various applications. We can make the composite membrane by coating or dense layer or the porous support. So you can make this by dip coating and spin coating. So here you can see this dip coater. You can put your membrane, means fixed membrane here, and you can just like dip in a solution. So dipping speed, dipping time, and the lifting speed, basically they decide what is the thickness of your coating on your membrane. So here you can see this is the porous support, and this is some non-woven support, and here this is a top layer that you have coating over it. So this can be used for this pore penetration, and to avoid this pore penetration, there are like pre-filling and some other part, so that can be worked for your membrane. Another maybe this spray coating. You can use this technique to coat your target like this. So here you can see this is the selective coating on this surface that can be also used for making it thin selective layer either on dense or any pore support. This is the example of spin coating. So here what you can do, you can just pour your solution here, and you can have the different speed in terms of RPM. So you can control the thickness of RPM. Once you are going at higher RPM, there is a certain chance that the thickness of your deposited layer, it may be around few nanometer. But if you are in low RPM, of course, you can deposit in micrometer thickness also. Another possibility, like we can use a plasma polymerization to make this membrane. Here we do this ionization by the dissociation of molecules and bonds. One final possibility, like in case of dense membrane, you can make them composite. So for example, we have used here multi-wall carbon nanotubes. So if you are mixing them randomly, they mix like this. But if you are using some field or in magnetic field, we have tried. So we tried to align them in perpendicular solution. So in right hand side, you can see this is a petri dish putting in this field. So in this way, these nanotubes, they are aligned perpendicular to the membrane. Okay, and this is some primary measurement that confirmed that carbon nanotubes are there. Then we use this palladium nanoparticles synthesis, and we use this palladium nanoparticles in CNTs. So because of this palladium, we had very good absorption of hydrogen and other gases going out. So this way we can make a selective membrane by using this nano composite. So here you can see this pits that is marked circle. So basically these are the opening of your nanotubes over the surfaces. Okay, so in next 5 to 10 minutes, I just discuss another polymer, that is the block copolymer. So this is different in normal polymers, like if we mix polymer A and polymer B. So when this go and macrophase separation, so like these polymer mix randomly like this. But when we have using this block copolymer, like polymer A and B, so they are coming in a particular pattern like AB, BA, AB, and so on. So these are the various fraction of this block, means A and B. So here you can see this sphere, cylinder, lamella, and there are so much morphology that we can make by just making different variation. So by changing, if you can see this red polymer, so how this morphology is changing, and here by changing this blue part, so you can see how this morphology is changing. So these are the various morphologies that can be possible in block copolymer membrane, but particularly if we are interested in our filtration purpose, so in cylinder that are perpendicular to the surface, this may be our interest. Okay, so here we do not need any kind of ion beam or any other treatment to make them porous. So like we are using this PSP4BP polystyrene based membrane. So simply by we can using this spin coating, then we can have the solvent annealing, and what happening, the another component of polymer that can be washed out. So here you can see like there are two polymer A and polymer B. Polymer A represented by red and blue. So what is happening, this polymer A red that reacts with the additive, and later on we can remove this additive by like any ethanol and methanol and so on. So this part goes away, and here you white that basically denoted the porous channel that is available, ordered porous channel. So here we can maintain the ordering, even we can maintain the porosity by changing different molecular weight. So by making, and one most interesting part that is in this block of polymer, like once we prepare the structure that is the perpendicular, and later on realize, okay, I don't need this, I want this. So just you reverse, put in another solvent. So you can see this perpendicular morphology that can be converted to this. And if you have this morphology, you can tune like this. Once you remove the another component additive, then you cannot switch. So as I told, means I'm basically for our interest, this is, you can see a well-ordered array of hexagonally arranged this block of polymer nano templates. So they can be used for a selective membrane for means for gas and other, but only the part, these block of polymer, they are very expensive, and the thickness that you can see here on any substrate, that was around few nanometer. So means if we are making a self-supported membrane from block of polymer, this is very costly. And if we are going very thin, so it does not have mechanical strength so that we can have such operations. Okay, another part that may be all interesting, that is the conjugate polymers that can also being used for the gas separation. Basically, they are the conducting polymers, and they can also have, you can apply some biasing, so that means there are opening of certain chains, and this way you can have a selective separation for particular gases. So this is just an overview of these membranes that are being used for the gas separation, different type of membrane that may be hybrid, organic or inorganic. So organic may be biological constituents, polymeric membrane, inorganic, ceramic, zeolite, silica, carbon, and metal oxide membrane, so on. And these are the factors, so how we recognize a good membrane that should have high permeability, diffusivity, solubility, and selectivity, long-term stability, and these are the advantages of membrane over other technology that being used for the filtration. Okay. So this is a schematic diagram. I'm just discussing because of this porosity. So here you can see if you have large pore This is 0.1 to 10 micrometers. So every gas is passing through. Here you have a high permeability, but of course low selectivity. But here you can see the porosity is slightly less than this. So only one kind of gas that can pass comfortably, and other can be blocked. And here this is molecular sieving, very less pore distribution. So here you can see only this blue part is coming out, and this is the solution diffusion in case of pore, means dense membrane or composite membrane. So what is happening here, there is no pore, but this gas is being absorbed at this high pressure side and then dissolves from the lower pressure side because of this pressure gradient. So this is a schematic diagram for any gas permeability or gas separation setup. So here we use this polymer membrane. Here we apply higher pressure. This is the downstream pressure that coming to flow meter. And this way we can calculate what is the flux that is coming out of, from this membrane. And again, just for, please remember this kinetic diameter again. Here we written in the angstrom order. So you can see apart from hydrogen, these are very close to each other. So what are the way how we can separate them? And these are the gas permeability setup that is available in our lab here in MNIT Jaipur. So for dense membrane, this diffusion permeator, and porous membrane, that's a self-developed setup that we can do. So in case of track-assist membrane, where we have such size, nice pore distribution over the surface. So here you can see once we are increasing the etching time, means we are removing, and the other part, the permeability is increasing and it is going very high. This is particularly for hydrogen, but at the same time, means once we have sufficient porosity in the sample, you can, the selectivity, this is not good. So what we can do? Another part that we can do, we can make a composite. So here we tried with the random, we try this aligned. So you can see in case of aligned CNTs is better than the pristine one. And then we tried some palladium nanoparticle deposited here. So these membranes, they are better than the others. Another what we can do, this block of polymer nano template. So here we have this porous membrane and try to cover having means low concentration solution. We try to spread them and then we check our porosity of this. You can see the support membrane. You can see this pore, they are not completely covered by the upper layer of block of polymer membrane. Once we tried with the higher concentration of this block of polymer, you can see there are cracks in the surface. So it means we have to optimize what is the concentration needed of this block of polymer template to cover the support membrane. Finally, we could optimize the parameters. And here you can see we try to cover this nano template, support membrane by using this block of polymer template. This is the support layer having 0.1 micron porosity, and here the support is 0.2. So here what you can just figure out that supporting membrane that has higher porosity as well as mechanical strength, this support this block of polymer. So upper layer basically that help us to get a more controlled way to diffuse the gases in these nano channels, and the supporting layer basically providing us a mechanical strength. What is happening here because of this narrow size pore distribution again, so our this permeability this drastically goes down. So this is like earlier it has 204 and here it's 11, 43 and 2.4. So basically this is membrane behaving just like a dense membrane. So what we could do, again, we tried different molecular weight, and like before having a perfect arrangement before annealing and after annealing, and then we try to again measure the gas permeability for different molecular weight. And here you can see the molecular weight that denoted by 205 and anil, they have the higher permeability in comparison to the molecular weight that is 13.9. Okay, so means what we can do, like once we prepare the channel and we do the etching, we prepare this nano template. So what is the means how we further can improve? So this is another possibility that we found, like this is a very good way to functionalize them and depositing the nanomaterials that is the gas sensitive. So here you can see this is the channel that is already created. So suppose here, if I'm talking about this microbe size membrane, so this channel has a micrometer size and you functionalize them, then you can put your gas sensitive nanoparticle inside this channel. So what will happen, the active diameter of channel reduces, at the same time the more gas that can be diffused within this nanomaterial. So this may help to get the better selectivity. So we tried with our this membrane that in trackaged, where we are unable to control the selectivity. So this is some process that called the carboxylation and then amination. Carboxylation means having this COOH group and this amine NH3 group, and then we further deposited this palladium. So in pristine PET membrane, there are few carboxylic groups, so attachment is very limited. But when we further carboxylated, so the more attachment of this palladium nanoparticle, and in amine, you can see a lot of, because it has more ability to attract this palladium nanoparticles. So did XPS, and finally you can see from this TM image, this is the aminated membrane. So this more bright part, that is because of palladium. So you can see more number of palladium nanoparticles, they are on the surface within the pore, and most of the pores they are blocked in cases of this aminated membrane. This is the term repelica. So just to say the presence of your palladium nanoparticle over the surface. So what is happening here? So most of this hydrogen, they are being absorbed within this palladium nanoparticles. So permeability goes down, but at the same time, the selectivity, because it is not affecting the permeability of carbon dioxide. So this way we are getting good selectivity of gases in aminated membrane. The similar part we tried in our carbon nanotubes also. We functionalized this carbon nanotubes, and then we deposited the palladium nanoparticle in CNTs, and then we aligned them in a polymer matrix. So such membranes are also useful to have better selectivity. So we tried to increase, because earlier we did the random functionalization. So we tried for different 6 hours, and then you can see here, this is for different timing. So as we increase the time, so this brightness means this, you can see like more palladium nanoparticles, they are depositing over the surface. So it means the attachment of this palladium nanoparticle in this functionalized membrane that helps us to control the selectivity of the gases. Here you can see, like earlier in pristine membrane, the selectivity means the ability to pass a particular gases that was around 2.53, and that we can address up to 3.72, and here from 3.3 to 6.05. So certainly it helps in trackage. Similarly, we tried the concept in this block of polymer nanotemplates. So we have the same strategy in carboxylic, then amine, then we binded this palladium nanoparticle. So when we have both layer, means supporting layer also with palladium and upper layer also with palladium. So here you can see the selectivity of gases that increase drastically from this to this up to 48 hours. And this, you can see the template, and the white part, if you can visualize on a screen, these are the palladium nanoparticles. They are around this block of polymer nanotemplates. So in conclusion, we use our membrane in hydrogen separation. So these may be a advanced polymeric membrane, or this may be modified membrane with optimized parameters. These maybe this ion implantation, cross-linking, functionalization, microporous polymer. We can use different fillers that are the gas sensitive, and we can certainly use this kind of membrane in for our fuel cell application, or particularly to either capture the hydrogen so that other gases they are going out, so we can make a hydrogen selective membrane. So in conclusion, just the functionalization of membrane and nano templates that help to control the permeability and selectivity. This composite membrane with the oriented pores that can also be helpful to controlling this permeability and selectivity. So both can be improved. In generally, when talk about this polymer membrane, so basically they have the trade-off relation, means once we increase the permeability, other can goes down. So both can be improved. So just I want to acknowledge my mentors where I have learned this process: Professor Y.K. Vijay from University of Rajasthan, Jaipur, Professor Ashutosh Sharma from IIT Kanpur, Professor Manfred Stamm from Dresden, Germany. So we tried to learn this different membrane application, and we have collaborated in membranes. Professor Volker Habits from University of Hamburg for this block of polymer, Professor Mim Han-Yoon for this composite membrane, and particularly in case of conjugate polymers, Dr. Vaibhav Kulthrist in Bhavnagar. And the work that I have presented, this is from Dr. Rajesh, Dr. Kamakshi, and from Ms. Michelle Seni. And for the whole work, we could get funding from different sources: DST, Inspire, SERB, IUC, and Humboldt Foundation. Thank you very much for listening to me and your patience. I'm happy to answer your queries, please.
Thank you so much, sir. It was such a nice, informative session. Participants, if you have any question, you can put them in the chat box. Meanwhile, sir, I would like you to please give some information like or the material testing facility that we have in MNIT Jaipur, how the researchers can get their samples tested there, what are the facilities available, and what are the charges, like from where they can get all that information.
Okay. So maybe I will again use your screen. So we have a dedicated portal like MRC MNIT Jaipur. So if you are visiting our web page, so here you can, I'm just trying to no. Can you see my screen now?
No, sir, only your slides are visible.
Okay. Just a minute. So can you see now?
No, sir. I guess you need to stop sharing your PowerPoint presentation. Yes, sir. Now it is visible, sir.
Okay. So this is a new portal, mrcmnit.ac.in. So here, this is the Center Research Facility
Now
tab.
it is visible, sir.
So from this tab, you can see the list of facility. They are available here. You can see their capability and their charges. And here, second tab. So this shows how you can use the MRC facilities, means how you have to register here as an MRC user, and then you can book your preferred slot. So these are the facility charges. They are mentioned here. And here you can see the current status of equipment, which is working or not working. And this is your online booking calendar. So here you can select the equipment. So for example, if I am selecting any random, like for example, this scanning electron in UTM. So you can see this green one, they are basically this is for TEM. So red one is already booked. And if you see anything that available with green means these slots are available and then can be booked by anyone from anywhere. Okay. So energy
Yes, sir.
application of these nanofilters, particularly in, I have talked about this hydrogen energy. So like when we are having this multiple gases, so how we can purify the hydrogen, or how we can make a membrane that is particularly selective to hydrogen. So if we have this functionalized polymer membrane that is having palladium or platinum, so they can particularly absorb the hydrogen and other gases can go out. So this way we can make these membrane for energy application.
Thank you so much, sir. Thank you so much for giving such nice explanation. And I'm sure that our participants have also noted down the testing facilities available at MSIT Jaipur.
Maybe I can just, I'm just writing in the chat box. So if somebody interested,
Yes,
they
sir.
can visit this.
Thank you, sir. So thank you, everyone, for joining this session. I declare end of this second session of the day. Thank you so much, everyone, for joining. Thank you so much, Kamlendra, sir, for sparing your time with us.
Okay, thank you, ma'am.